This is problem set number 3, problem 6. A quantity of air is taken from state A to state B along a path that is a straight line in the PV diagram. For part A, in this process, does the temperature of the gas increase, decrease, or stay the same? Explain. Okay, so for part A, we know that a certain quantity of air is taken, right? So let's write down our ideal gas law. PV equals nRT, right? What is constant here? That quantity of air, the amount is constant, or moles, and the R, these are both constants, right? Okay. So if these are constant, the value of the temperature on the right side of the equation right here depends on the factor between the pressure on the left side of the equation multiplied by the volume on the left side of the equation. All right? I just wanted to point that out. So, if we look at the PV diagram that's given, we see that we have a value for volume at state A and a volume at state B, right? And it's obvious that the volume at state A is less than the volume, let me say, okay, the volume at state A is less than the volume at state B, right? Because it's on the left side. See, so it's less than volume at state B. Okay. Oops. And the same, our pressure at state A is less than the pressure at state B. Okay, so pressure at A is also less than pressure at B. So, as a result of that, if we look at the left side of the equation, our P times our V, which, because N and R are constants, is directly affecting the temperature on the right side of the equation. We can say that because pressure at state A and multiplied by the volume at state A is less than the pressure at state B multiplied by the volume at state B. Again, that's here on the left side of the equation. Therefore, that will affect the temperature on the right side of the equation. Therefore, the temperature at state A will be less than the temperature at state B. Okay? So, does that mean the temperature of gas increased, decreased, or stayed the same? Well, if our temperature at state B here, remember this goes that way. So if our temperature at state B is greater than the temperature at state A, so that means that the temperature of gas increased. Okay, that's the answer for part A. Okay, now moving on to part B. I'm just gonna copy this PV diagram and bring it up. All right, so this is part B. All right, what is the values given? We know that VA right here is equal to 0, VA is 0.0700 cubic meters. VB, volume at state B, is 0.1100 cubic meters. Right, so that just goes like that. the pressure at state A is 1.00 times 10 to the 5th pascals. Okay, that's pressure at A. So that goes that way. And pressure at B is 1.40 times 10 to the 5th pascals. That's equal to pressure at B. All right. So let's recall that the work is equal to the area under the PV curve. PV curve, right? The PV diagram. So what is our area? It's this rectangle right here. And the other area, let's use gray, is the triangle right here, right? So we have two areas we need to add together to get the total work done by the gas in this process. Right, so for part B, if volume A is 0.07 cubic meters, volume B is 0.11 cubic meters, pressure at state A is 1 times 10 to the 5th pascal, and pressure at state B is 1.4 times 10 to the 5th pascal. What is the work done by the gas in this process? So the work done by the gas, also assume the gas is ideal, right? So we can see that because this goes this way, or our volume increases from state A to state B, that means that the work of the gas or work of the system is positive since volume expands, right? And what that means is the volume at state B increased from the volume at state A, right, where we started. Okay, so anyways, let's calculate the work done by the system by calculating for the two areas here. One is the area of the rectangle, which is base times height, and the base is volume at state B minus volume at state A. That's this part, multiplied by this height, which is just the pressure at state A. Okay, so this is the area of the rectangle. Okay, and we'll add that with the area of the triangle, which is 1/2 base times height, and the base is also volume at state B minus volume at state A, and the height is the pressure at state B minus the pressure at state A, which is this region right here, right? Okay. So that's area of triangle. So let's plug in our values. And that is 0.1100 cubic meters minus 0.0700 cubic meters multiplied by 1.00 times 10 to the 5th pascal plus, I'm gonna move this here, okay, oops, I'll just delete that and add that, okay, and then the area of the triangle, that's 1/2, again, VB minus VA, which is just this guy. Times PB minus PA, which is 1.40 times 10 to the 5th pascal minus 1.00 times 10 to the 5th pascal. Okay, So you can plug that in your calculator and you will get, again, don't forget that we'll get 4,000 meters cubed times Pascal plus 800 meters cubed times Pascal, which actually meters cubed times Pascal is equal to joules, right? And that is because, I'll write it in blue. So again, recall that a Pascal, the unit Pascal is equal to the unit kilogram over meter times second squared, while the unit for joules is equal to kilogram meter squared over second squared, right? These are interchangeable units. So if instead of Pascal, I use meters cube times Pascal, which is kilograms over meters times second squared, right? This would cancel out, and I would be left with kilogram meter squared over second squared. Voila, that's just joules, okay? So my work done by my system, or work done by the gas, is 4,800 joules. That is your final answer for part B.